Hey guys, so me again. Hopefully you are all enjoying your day-ish off. I'm sitting here sick, so I will try my best to get through these next couple of lectures, but for right now we're going to do some video lectures. So just as a reminder for ourselves, we should remember a couple of intermolecular forces. Intermolecular forces, the ones we've got are ionic. We've got dipole-dipole, or as I like to call it, dip-dip. We have kind of a subsection of dipole-dipole called hydrogen bonds. Again, we call them hydrogen bonds because it is just an attraction, it's not a real bond. The last one we have is dispersion. We should remember that ionic intermolecular forces occur between ions or ionic compounds, whereas dipole-dipole forces and hydrogen bonding forces occur between polar covalent molecules. The last one, dispersion, is for nonpolar molecules. We think that nonpolar molecules have this induced dipole where they force themselves to shove electrons to one side of the molecule to create a slight, very tiny partial negative, and on the other side of the nonpolar molecule we create a teeny tiny partial positive. So we should remember from a previous lecture now that the idea of like dissolves like. We should also remember that when we think of these intermolecular forces, they have something to do with boiling point and melting point. Now, when we're talking about interactions, we think of the three main types of molecules. We think of ionic, we think of polar covalent, and we think of nonpolar covalent. We should remember the idea that like dissolves like. So we can think then that polar does not like nonpolar. We think that polar loves ionic. Polar also loves polar. So when we think about this, nonpolar, the only type of molecule that's going to interact nicely with nonpolar is nonpolar. Meanwhile, polar molecules can interact nicely with other polar molecules as well as ionic molecules. So we can think about these forces now as being the kind of idea behind the idea of solubility. When things are soluble in other things, when we think of solutions, we should remember the idea of solutions. We have a solute, some solute dissolved in a solvent to create a solution. Now, when we think of things in solution, a lot of times what we think of is maybe salt water. We think of things like salt water. We think of salt, sodium chloride, and we think of water, H2O. Now we know that when I put salt in water, they do interact nicely because salt does dissolve in water. So I know this ionic compound interacts nicely with this polar covalent compound. Now we think, again, we talked a little bit about electrolytes. We talked about electrolytes and we think, well, what does this salt do in water? We think this ionic compound breaks apart in water to form ions, which we also called electrolytes. Now, when we think about electrolytes, we talked about three different types. We talked about strong electrolytes, weak electrolytes, and non-electrolytes. Strong electrolytes, we remember all of them dissociate to form ions, whereas weak electrolytes, maybe only half of them dissociate in solution. Non-electrolytes, on the other hand, do not dissociate at all. They are usually covalently bonded molecules. Our best example here was sugar. A covalently bonded molecule that it's all stuck together, but in water will not dissociate into ions. Instead, it'll just swim around in water nicely. It will have nice interactions. Now, the reason for that is because sugar is also polar. We should remember that water does not only like ionic, it also loves polar covalent molecules. So now, we can think about these ionic compounds. We're going to focus really on these ionic compounds and think, well, if I have some amount of sodium chloride, we should remember molarity, talking about some amount of solute per some amount of solution. Let's just say that I have 0.025 molarity sodium chloride in solution. I can think that I have 0.025 moles of sodium chloride per 1 liter of solution. Now, when we're talking about molarity of these ionic compounds, what I can think of is, again, in my bucket, if I have 0.025 moles of sodium chloride per liter, that means what I've got here is actually 0.025 moles per liter of sodium remember that in solution, that sodium and chlorine break apart from each other. So really what I have is for every 1 mole of sodium chloride, I will get 1 mole of sodium and 1 mole of chloride. So I've got 0.025 moles per liter of sodium. I also have 0.025 moles per liter of chloride in solution. So we can go now to the slide, the let's think slide, where we're saying, all right, one question is, what is the concentration of sodium in solution of a 0.0025 molarity sodium chloride? So that's question number 1, pretty similar to the one I had up here, but let's think about it. So it's asking me, what is the concentration of sodium plus in a solution of 0.0025 molarity sodium chloride? Now, I should note 0.0025 moles of sodium chloride per 1 liter of solution. That's really writing this the exact same way, just with slightly different units again, but it's the exact same as saying 0.0025 molarity sodium chloride. Now, if I think about it, I know that in solution, my relationship between moles of sodium chloride and moles of sodium is 1:1, because again, sodium and chlorine come together in a 1:1 ratio, so when they break apart, for every 1 sodium chloride, I will end with 1 sodium and 1 chloride. So 1 mole of sodium chloride results in 1 mole of sodium plus. Now, when I come up with some answer here, moles of sodium chloride, I should end up with the exact same 0.0025 moles per liter Na plus, my sodium plus, which again is the exact same 0.0025 molarity sodium plus. All right, so that's pretty easy, but now we should be thinking about the second question. Well, what is the concentration of chloride in a solution of 0.000345 molarity Mg2Cl? Whoopsies, MgCl2, my apologies. So, I should be thinking here. I've got this solution, 0.000345 molarity MgCl2. Now I should note, in solution, whenever I have 1 MgCl2, this is going to break up into 1 magnesium and 2 chlorides. So when I'm thinking about the concentration now, my ratio of magnesium chloride to chlorine is going to be a 1:2 ratio. So 0.000345 moles of MgCl2 magnesium chloride per 1 liter. Again, I'm using the exact same number up here. The only difference is instead of molarity, I'm using moles per liter so that I can figure out my ratio between moles of magnesium chloride to moles of chloride. So I set up this little table here. I know that I have, for every 1 mole of magnesium chloride, I actually have 2 moles of chloride ions. So when I multiply and divide this all out, I end with units of moles of chloride per liters of solution. So doing my head math here, let's see, 0.000 times 2 would give me 690-ish moles of chloride per liter, which again is the same thing as molarity chloride. And you should note again that this number is now doubled to find the concentration of chloride in my solution. All right, so that was just a kind of brief reminder, or refresher on molarity. Now, going back to the idea of solubility, we should remember my electrolytes. We again should remember that strong electrolytes and weak electrolytes, they're both ionic compounds, but some of them seem to completely dissociate, while some of them only slightly dissociate, where half of them dissociate while the other half just kind of gets stuck together, maybe because they're held together stronger. Now, when we think of solubility, we have a couple of different words to describe something that is soluble, insoluble, or we can say miscible or immiscible. Two substances, A, and I'll call this, let's say, B. A and B. Now, if A and A have stronger attraction than A and B, we say that A and A are going to stay together and they are not miscible in solution. We say that if this attraction here is stronger than A to A or B to B, we say that they will mix, and we call that miscible. Now, we can also think of the idea of hydrophilic versus hydrophobic. We talked about how solutions many times are made with water. So when we think of hydrophilic, we think of water-loving substances which will be soluble or miscible in water. When we think of hydrophobic, we think of substances usually that are non-polar, because again, we remember the idea of like dissolves like. When we think of non-polar molecules, we think of things that do not like polar substances, water being a very polar substance. We know that they will not mix. Now, when we think about solubility, one other idea that we should be thinking of is the idea of saturated versus unsaturated solutions. When we think of an unsaturated solution, what we can think of is, say, a cup of water. Now we have this cup of water and I add a little bit of salt and it dissolves nicely. When I have this salt dissolving nicely, I decide to add a little more salt, and that salt dissolves as well. I'm going to keep adding salt until I get to a point where, well, the salt is clumping up at the bottom of my water cup, and there's no more salt that's being able to dissolve. We say that a saturated solution is a solution in which no more of that salt can be dissolved, or whatever substance we are trying to dissolve in water. Now, when we think about these reactions now, or the idea of these salts mixing or water mixing with different substances and solutes and solvents, one thing we should be thinking about is precipitation. Now we should remember from lab what precipitation means. Precipitation is the process of creating an insoluble salt by mixing two soluble salts together. Now, when you look at the slide for precipitation, you should see a couple of examples. We see the first example is Ag. NO3, also known as silver nitrate, plus sodium chloride, NaCl, sodium chloride. I produce now silver chloride, AgCl, and I also produce sodium nitrate, NO3. Now, one thing that you should note that is being boxed in this is this guy here. You should also note the phases. The phase, aqueous, AQ, we should remember means dissolved in water. Now that aqueous tells me this solution here, if it's aqueous, I know that in solution I've got silver plus and I've got nitrate negative, because again, anything that is with an aqueous tag there, aqueous phase means it is dissolved in water. Any ionic compound dissolved in water, we should now know, breaks apart to form ions. So I have this guy here, sodium chloride, my table salt. I should know at this point that that is soluble. It is aqueous, and I have sodium plus, and I have chlorine minus. Now, what I did is I took these two buckets here and I mixed them together, and I found that this thing here turned into a solid. What we say is that it precipitated out of solution, or it formed a precipitate. This guy here, meaning when I mixed these two buckets together, this chlorine found this silver, they formed a solid. Now, this NaNO3 again has an aqueous for its phase, meaning what it is in solution is just my sodium ions and nitrate ions, just kind of floating around in solution. So, when we think about this, we should be thinking, well, why is it that this ionic compound was aqueous, meaning it dissociated in solution? This ionic compound was aqueous, meaning it dissociated in solution. This substance stayed aqueous, meaning it just dissociated in solution. Why is it that this one is so special that it decided that it would precipitate out of solution? And we get to the idea of our solubility rules. Now, if you go to the slide that has the solubility rules, it gives you a whole bunch of random rules. The first rule says most nitrate salts are soluble. So, nitrate, sodium nitrate, most likely soluble. Nitrate, silver nitrate, most likely soluble. Again, rule 1 tells me that most nitrate salts are soluble. Okay, rule 2, most salts containing the metal ions lithium, sodium, potassium, cesium, and rubidium, and the ammonium ion are soluble. So we can think, okay, if I have lithium chloride, I would most likely say that that is soluble. And when I'm writing some equation, I would call that aqueous because, again, if it is soluble, we think this ionic compound will fully dissociate in solution. Now, these rules that you have here will be given to you on an exam. Do not worry about memorizing these, but you must know what they mean. So, for example, when we think about number 6, let's say, or you know what, let's look at number 4. Number 4 says most sulfate salts are soluble. Most sulfate salts. So if I think about this, sodium sulfate should be soluble. Now it says here that there are notable exceptions. Notable exceptions, we said this is aqueous again. Soluble means that it will dissociate in solution, but notable exceptions now are barium sulfate, for example, BaSO4. The exception, meaning that it in solution actually will not dissociate, so we would call this a solid. Now, these solubility rules, one more time, will be given to you on an exam, so don't worry too much about memorizing them, but you should know, again, what they mean. Now, if you look at the next slide, it actually gives you a good overview of how these precipitation reactions work, and you should note or remember how these work from lab. In lab, we actually did these experiments. We actually did some of these precipitation reactions to determine whether some ion was present in solution. One that we actually did is the silver nitrate test to test for chloride ions, because we know that silver chloride does not stay in solution, it will precipitate out, and so we can test for chloride ions in any solution by adding silver nitrate. So kind of cool to think about that. Now, when we think about solubility, something neat to note is that solubility of salts, we should know this already by working in the kitchen, solubility of salts or ionic compounds actually goes up as we increase the temperature. So if you've ever tried to dissolve sugar in water, and the first thing you should be thinking is, well, let me put it on the stove. Heat up the temperature of the water and more of that sugar will dissolve. Salt water, same thing. You increase the temperature and you will increase the amount of salt that you can dissolve in water. Now, actually, gases, on the other hand, while solids will increase in solubility when you increase the temperature, gases' solubility will actually decrease as you increase the temperature. Now, when you think about that, that doesn't seem like such a great thing for the fishies. We remember that fish in the ocean actually survive because there's gaseous oxygen that's dissolved in the water. Now, we go back, way back, kind of throwback Monday today, or whatever day it is, and we think, well, we have this issue of global warming. Now, global warming is talking about overall increasing the temperature because of the amount of CO2. Now, okay, we think about increasing our global temperature and they're like, well, wait a second, if we're increasing our temperature, the water temperature is also going to be increasing. Okay, when we increase the temperature of water, that means that less and less gases are going to be dissolved. When we think less and less gases dissolve, that means that the oxygen that these fish survive on will actually be leaving the water as our global temperature increases. Means that fish are going to be dying, which is kind of scary. All right, so now we should be thinking about these precipitation reactions, and when you're doing your worksheet number 10, you should be working on worksheet number 10 using the table, slide number 71, the solubility rules table, that you should be thinking about in this reaction. What is going on? What players do I have? Are they all soluble? And do I form a precipitate? So that's kind of going backwards a little bit. Now moving forward, the last couple of slides we have here, water treatment. Thinking about our water and where it comes from and what we use, we actually use a couple of different methods for water treatment, and one of them is a solubility reaction or a precipitation reaction. If you look at the reaction, we have aluminum sulfate reacting with calcium hydroxide to produce aluminum hydroxide and calcium sulfate. This reaction actually helps to remove clay and dirt from our water. We have charcoal filters, we have chlorination for antibacterial purposes, fluoridation for teeth purposes, and our water is treated again through some of these precipitation reactions. Now, one other way that we work with water, and again, this whole chapter was about water to begin with, we actually have this process of water desalinization, which is the process of trying to remove salt from water. We use a process called distillation, which is actually the boiling of water to really just take the water away from the salt. So instead of trying to filter out the salt, what we do is we try to filter out the water. We boil the water, leaving the salt behind. We collect the boiled water, cool it back down, and try to collect that water. Kind of cool. The last process we have for water desalinization is osmosis and reverse osmosis. And basically this is the process of taking water and using semi-permeable membranes to actually filter out some of the salt that we have in salt water. Now when you think about it again, it's kind of the process of filtering water rather than filtering salt, but regardless, it's a cool process using pressure to desalt or desalinize our water. Kind of sweet. Alright, so that's pretty much it for Chapter 5. Again, you should be going on to Chapter 6 lecture just to start it, the video lecture, and we will continue on Wednesday. Have a good rest of your day.